Dynamic indexing. In this lecture, I will consider two dynamic indexing methods. First is document indexing. In this lecture, I will consider two document indexing methods, MapReduce and dynamic indexing. So first we will go through the MapReduce. Actually, MapReduce is a programming model and used to handle a huge volume of datasets. MapReduce can be explained as a two-step process, map and reduce. But before going in detail, first I will go through a simple example and explain how map and reduce system works. In this example, suppose in the map reduce there exists generally first is map function, and other but less important part is shuffle or shuffling, and other part is reduce. So in map function, suppose we have millions or billions of documents, and suppose it contains words like the, document, etc. And documents are represented as D1, D2, D3, and so on. Now the map function, the major part of the map function is it takes the input from text and then prepares the inverted index. For example, the exist in document 1, again word document exists in document 2, like that. And after that there is a shuffling part which is generally hidden in entire definition of map reduce, because map reduce actually maps and then reduce. So now the mapper function, actually this is a single part of mapper function, but actually map function contains a lot of terminals and it divides the task into several terminals. For example, it handles suppose from D1 document D1 to DK through terminal D1, means it will be clear, like it handles document D1 to DK task through block or cluster C1. Similarly, DK plus 1 to something to cluster C2, and this is called mapping. It identifies that how many times the occurs, how many documents contains the term the, suppose document 1, 2 and 5, and so on. Similarly, how many times documents, how many different documents contain term documents, suppose 11, 20 and etc. Now the work of shuffler starts. Several such clusters will create such kind of separate indexing or inverted index. Now the term of work of shuffler starts. Now the shuffling part will do, it will pass the data to reduce page in such a way that suppose reduce page contains some clusters C1, C2, C3, etc. So after that it will pass, shuffler actually selects the particular keyword, for example the, and send to all the related from different channels, from different clusters. Suppose this is from cluster C1, it picks the word the and send to the reducer cluster C1. From C2 it picks the cluster picks the information related to the and send to reducer C1. So this is the shuffling part. It assigns the particular task to particular reducer to just reduce the time complexity and speed up the processing. So suppose there are 100 different such kind of terms exist, and there are 10 such kind of reducer clusters. Then shuffler you can write a different program or to balancing program also. Actually, writing code for shuffler depends upon your requirement. If you want some balancing, then you can divide. You can write shuffling programs in such a way that it can identify some near about equal load to all reducers. And after that, the task of reducers start. It reduces the entries to a particular common inverted index. For example, suppose from C1 the information comes like D occurs in the documents 1, 2 and 5. From C2 the information comes like D occurs in the documents 7 and 30. So reducer will reduce this information like that. D occurs in the documents 1 to 5, 7 and 30 like that. This is the work of reducer. Mapping means it maps the document, the term and document ID. This is a simple example of document indexing by using map reduce function. So mapper just creates the document term and document index. Then it provides the entry to shufflers. Shuffler just shuffle the task in such a way that to reduce the load and improve the efficiency, and then provides the task to reducer. Reducer will reduce the number of such frequent entry and provide a perfect term document indexing. So this is a simple example of map reduce function. Now it will be easy to understand how actually map reduce system works. So map reduce is a programming model because each part is flexible. You can write your own code to control every part, mapping part, reducing part, and in between mapping and reducing there is a shuffling part. Used to handle a huge volume of data set, map reduce can be explained as a two-step process known as map and reduce. Map function is a user-specified function, takes an input pair and produces a set of intermediate key value pairs. The map reduce library groups together intermediate values associated with same intermediate key and passes to them to reduce function. Just I discussed. And reduce. The reduce function also written by user accepts the intermediate key 1 and the set of values for that key. It merges together these values to form a possibly smaller set of values, typically just 0 or one output value is produced as per reduce invocation. The intermediate values are supplied to the user's reduce function via an iterator. This allows us to handle a list of values that are too large to fit in the memory. Now the map reduce index construction was just one page. Take term, prepare term and document index. Another page, transforming term partitioned index into a document partitioned index. Term partition means one machine handles the subrange of terms. Document partition, one machine handles a subrange of documents. As well, I discussed in the web part. Most of the search engine use a document partition index. Better to load for load balancing. It's document partition indexing, like already discussed that we take a bunch of documents, pass through some mapper function, map cluster, nodes, is a document set 1. Similarly, set 2. This set will pass through this. This will be. This is a. Every set will contain some fixed amount of documents. So every set will contain some fixed amount of documents. For example, suppose it contains 10 to the power 5 documents. This contains 10 to the power 5 documents. And applied and simple indexing, like suppose Word, the how many documents it contains. Word, suppose you want to, then mapper will manage this kind of operation. This is called document partition operation. So most of the web engines use such kind of document partition based system. Now the schema for index construction in MapReduce. I already discussed that how can I prepare the different schema for MapReduce. For example, map function will take input list vk and reduce it like k into list v. Means suppose we entry like the number of the document id which it contains 1, 2, 3. Now k represents the document term id and v represents the list of document id. And suppose there is another list like it occurs in document 5 and 9. Then reduce function will reduce it like that, the represented by this list and b represents 1, 2, 3, 5 and 9 like that. So this is the output, reduced output. It reduces the frequent occurrences of p. This is MapReduce. Actually, it looks very simple operations, but for huge billions and trillions of documents, when we divide the entire task into several different machine clusters or apply some distributed computation, and actually MapReduce function is used with distributed computations and speed up the document indexing task, and we can assign several other such kind of tasks. For example, instructions of schema for index construction can be given as map function collection. It collects the list of all term id document id and reduce multiple term id and document ids into posting list 1, posting list 2, and every posting list will contains such kind of reduced information. For example, map the documents. You can take as an exercise like suppose D1 contains C, K, and C's edu. D2 contains C died. So C1, C, D1, name D1, C D1 means C contains C exists in D1, K exists in D1, C exists in D1, and C's exist in D1. Now in D2, C exists in D2 and I exist in D2 like this. Now how can we reduce? So C exists in D1 and D2. So C exists in D1, D2 and D1. Died exists in D2. Again we can reduce like C exists in D1 2 times and D and C exists in D2 1 times. For example, C exists in D2 only 1 times, but here 2 times. So this is a sample reducing function. This is the simple MapReduce working example. Here the doc collection or input files are split into 5 sets, and each set provided some workers are assigned for each steps, and after that there is some user input program or sufferers which identifies or master control which provides assigns tasks to different computers or clusters. These are the intermediate files on local disk. So intermediate file will contain initial indexing, and after that it will provide some sufferers, and sufferer will check to whom worker machine, which worker machine should be assigned for which part of keys or which part of particular task, and then the reduce page works and then gives the output file. This is a very traditional simple machine. We can write our own code for map page, reduce page, and shuffling page. It depends upon the requirement of task and availability of system, capacity of the system, so that we can achieve the optimal quality of or optimal efficiency, optimize the efficiency of the system. There is a simple distributed indexing with map reduce. It splits the task into several subtasks or splits the file into several chunks or groups or sets. Then assign to parser. Parser assigns the segment files which starts with A to F, G to P, Q to Z, like that. There is a masters which are actually called, which we can call shuffler also. So masters, after that masters or shufflers assigns a particular file which starts with A to F with inverter 1, which results in some postings after reduce page. So this is example of distributed indexing with map reduce. Now the next part is the dynamic indexing. Thus far we have assumed that the document collection is static. This is fine for collection that changes infrequently or never. Example, Shakespeare's plays. But most collections are modified frequently with documents being added, deleted, or updated. This means that few terms need to be added to the dictionary and posting list need to be updated for existing terms. The simplest way to achieve this is to periodically reconstruct the index from scratch. This is a good simulation if the number of changes over time is small and the delay in making new documents searchable is acceptable, and if enough resources are available to construct a new index while the old one is still available for query. So now we can identify the dynamic indexing in this case, like generally concerns with a huge, sufficiently large database, as index-related addition, deletion, or updation operations are easy with small text collections. Important points: general trends with huge digital library or search engines, like documents come over time and need to be inserted, or documents are deleted and modified. This means that the dictionary and posting list have to be modified. First, posting updates for terms already in dictionary, new terms added to dictionary, auxiliary indexes used to, the major part is use of auxiliary indexes. If there is a requirement that a new document be included quickly, one solution is to maintain two indexes. First is a large main index and a small auxiliary index that stores the new document. The auxiliary index is kept in memory. Searches are run across both indexes and results merged. Deletion are stored in an invalidation bit vector. We can then filter out the deleted documents before returning the search results. Documents are updated by deleting and reinserting them. This looks very simple, similar to cache coherence, which we use in digital, which we use in computer architecture. Like first, we make some changes at cache level, then changes go to main memory level, and then disk level. But here only two levels exist. Some auxiliary index kept in memory. Some auxiliary index kept in memory. Searches are run across both indexes and results merged. Deletions are sorted as in invalidation bit vector. Means we do not delete immediately. We just make a bit vector 0, like this index doesn't exist, and 1 means index exists, like that. Each time auxiliary index became too large, we merge it to main index. So this is very simple. This is the traditional approach. Maintain a big main index. New documents go to a small auxiliary index. Search across both merge results. Deletion. Deletion creates the main problem. Suppose for this to solve such kind of problem, because suppose we delete a record from a huge bunch of record, then we require a lot of shifting of records. So best thing is use a bit vector based scheme that this exist or not exist, like that. So use a invalidation bit vector for deletion deleted documents. Filter doc output on search result by this invalidation bit vector. Means in case of search result, just check whether invalidation bit vector is 1 or 0. If it is 1, then we can search that particular results and then periodically re-index into main index, and we can merge the auxiliary list to main index by refining it. The major issues with main and auxiliary indexes: problem of frequent merges, the poor performance during merges. Some other issues with merging of auxiliary index into main index is efficient if we keep a separate file for each posting list. Merge is same as simple append, but then we would need a lot of files, insufficient for operating system. Actually, each time the auxiliary index became too large, we merged it into main memory or main index. The cost of this merging operation depends upon how we store the index in a file system. If we store each posting list as a separate file, then the simple merge consists of extending each post list of main index by the corresponding posting list of the auxiliary index. In this scheme, the reason for keeping the auxiliary index is to reduce the number of disks required over time. Updating each document separately requires up to m average disks, where m average is the average size of vocabulary of the document in the collection. With this auxiliary index, we only put additional load on the disk when we merge auxiliary and main indexes. Unfortunately, one file per posting list scheme is infeasible because most file systems cannot efficiently handle a large amount of files. The simplest alternative is to store the index as one large file that is as concatenation of all posting lists. In reality, we often choose a compromise between two extremes. We choose to simplify the discussion, we choose the simple option of storing the indexes in one large file, like that. So instead of using one big file to store indexes, use a scheme somewhere in between. Example is split very large posting list to collect the posting list of length 1 in one file, etc. Another thing is logarithmic merge. It maintains a series of indexes, each twice as large as previous one. At any time, some of these powers of 2 are instantiated. It keeps the smallest Z0 in memory, the larger one I0 to I1 on disk, and if Z0 gets too big, greater than n, writes to the disk as I0 or merge with I0 if I0 already exists as Z1. Either write merges Z1 to disk as I1 if no I1, or merge with I1 to Z2. Now it will clear from here also. Suppose we have a list, merge Z0 and token. If Z0 is already equal to n, then for I is equal to 0 to infinity, if I1 member of indexes, then merge Z1 is equal, then merge that index with Z1, where Zi1 plus 1, Zi plus 1 is a temporary index on the disk. Now reduce the index size, otherwise write that index on the disk. Merging technique is very simple. Suppose index I1 contains some terms index, term ID, and D1 is the document ID. Now, suppose size is too enough, size is too large in auxiliary list, then what to do? If I1 already exists in the disk with index Zi plus 1, then merges this list with that and reduce this, remove that, reduce this space. Otherwise, add index I1 with list, index list, and then it will increase the index list and merge and then break. Now Z0 is equal to, until we get this list empty. Now the logarithmic merge, this is the logarithmic merge adding tokenizer, means how to add tokens by using logarithmic merge. Now if Z0 is in memory index, Z0 is equal to 5, indexes is equal to 0, while do logarithmic merge add token indexes Z0 with next token, means we will apply this token, means every time if we fill that, if temporary index got filled, then we will repeat this process from the important points of logarithmic merge. Auxiliary and main index construction time is OT square, and as each posting is touched in each merge, logarithmic merge, each posting is merged in log t times, so complexity is O log t log t time, big OH of t log t times. So logarithmic merge is much more efficient for index construction, but query processing now requires the merging of big OH of log t indexes, where it is O1 if you just have a main and auxiliary index. Further issues with multiple indexes. Co-location-wide statistics are hard to maintain. Example, when we spoke with correlation, which of several correlated alternatives do we present to the user? We said pick the one with the most hits. Means this is actually a problem. For example, Such kind of problems exist, similar kind of problems exist in computer architecture, where we have a very a small space in register, and CPU fetches the data which doesn't exist in the register. So how to manage the data in register or main memory register pages, it requires some techniques like least recently used or most recently used type of things. Same kind of schemes are applied here. Let pick one with the most hits. And how to maintain the top one with multiple indexes in validation bit vectors. The answer may be ignore everything but the main index for such ordering. We will see more statistics in results in rank. Dynamic indexing at search engine. All large search engines now do dynamic indexing. Their indexes have frequent incremental changes, news item, blogs, new topical web pages. Due to huge increase in the size of news items and variations of news items, blogs, and topical indexes, only dynamic indexing is just dynamic indexing type of techniques is very essential for such kind of things. But sometimes, typically, they also critically reconstruct the index from scratch. Means after this lot of merge and means suppose document doesn't exist in our pool or index doesn't exist in the pool, then we prepare auxiliary index, put the indexing information there, and after that sometime merge, then it creates a lot of unused bit vectors which says that index is already deleted or the page is of no use, and such kind of deleted bit vector, presence of a lot of such kind of deleted bit vectors creates a lot of unused disk space. So to maintain such kind of problems, we require a periodic reconstruction of index from scratch. So dynamic indexing is dynamic in operations, but it requires some static operations also. Query processing is then switched to the new index and old index is deleted.